welcome you all in this course of Electronics Engineering, and the code of the subject is KOE038, and today we will discuss unit number 3 and this is lecture number 3. So before it started today's topic, let me describe you what we have discussed in the previous lecture. In the previous lecture, we have discussed about the transistor configuration, and we have seen in the transistor there are three terminals: emitter, base and collector. If one of the terminal is made common, that means transistor can be utilized as a two-port network. In the two-port network, we have seen there is one input port and the other is your output port. That means at the input port, we are able to apply the input. As far as output is concerned, output we can obtain at the output port. So in the transistor, if one of the terminal is made common, that means transistor can be used as a two-port network. Is that clear? So in the transistor, it is well known to all of us, emitter can be made a common, base can be made common, and you can also make collector as a common terminal. So depending upon which terminal you are making common, there are possibilities of three transistor configuration. First is common base, second is common emitter, and the third and the last one is common collector configuration. In the last class, we were discussing about the common base configuration, and we have seen how we can draw the common base configuration and how we can obtain the relationship, current relationship for the common base configuration. And we have defined a parameter, and that parameter is known as a current amplification factor alpha. But the value of alpha is lying between 0.95 to 0.99. So somewhere the current gain is less as far as common base is concerned. Now today we will focus on the common emitter configuration. That means emitter terminal is common for the base as well as for the collector terminal. So emitter terminal is common. Now firstly I am going to draw the common emitter configuration. Emitter is made common. So let me draw the common emitter configuration for NPN transistor. For NPN transistor. At your home, you can also draw the common emitter configuration for PNP transistor. Only voltage polarity is going to be changed. Type of majority charge carriers are going to be changed. If we will discuss about the NPN transistor, majority charge carriers are electron, but for the PNP transistor, majority charge carriers are holes. So here firstly, I will draw the common emitter configuration. That means emitter is common for the base as well as for the collector. So let me draw the common emitter configuration. This is N. This is depletion region. I am not going to show over here positive and negative immobile ions. Only for the sake of simplicity, I am just drawing it these lines, and this represents the depletion region. Now we are having P region. As it is well known to all of us, base region must be thin and it is lightly doped. This is base region. And again, we are having depletion region, and now this region is N. So here this terminal is known as collector terminal. This terminal is known as base terminal, and this terminal is known as emitter terminal. So this is collector terminal, this is base terminal, and this is your emitter terminal. As you can see, emitter terminal is made common. Emitter terminal is made common for the base as well as for the collector. So if you want to apply input, we will apply the input at the base terminal with respect to the emitter terminal. As far as output is concerned, we can obtain the output at the collector terminal with respect to the emitter terminal. Is that clear? So emitter is made common for the base as well as for the collector. Is that clear? So this is defined as a common emitter configuration. For all the configuration, it is well known to all of us, we will operate the transistor in active region. So for all the configuration, what is going to happen? Emitter base junction is forward biased and the collector base junction is reverse bias. Is that clear? So as far as this circuit is concerned, this is your emitter base junction, and the emitter base junction must be forward bias. Is that clear? So if this is P type region and this is your N type region, how we can make it forward bias? We will apply positive voltage at the P region with respect to the emitter terminal. That resistance is known as a RP, which basically used for controlling the amount of current. So this is defined as a current limiting resistance, and here this is positive voltage, and that is known as VBB. Similarly, as far as collector is concerned, collector with respect to the emitter, as you can see, this is N region, and the collector base junction must be reverse bias. This is collector and this is your base. Collector base junction must be reverse bias. So you have to apply positive supply over here with respect to the emitter terminal. So here N is positive with respect to the emitter terminal. So this is reverse bias, and that voltage is known as a VCC, and this is your current limiting resistor RC. As far as input is concerned, we will apply the input at the base terminal with respect to the emitter terminal, and we are getting the output voltage at the collector terminal with respect to the emitter terminal. So as far as output is concerned, the output is defined in this case is VCE. That means output at the collector terminal with respect to the emitter terminal. As far as input is concerned, we have applied the input at the base terminal with respect to the emitter terminal. So this is defined as a VBE, base to emitter voltage drop. One thing which is very important, you should always keep in your mind the base emitter voltage drop. If this transistor has been manufactured with the help of silicon, the VBE is equal to 0.7. That means if you want to make on input junction, if you want to make it on, you have to apply the voltage at the base terminal, which must be greater than 0.7 volt. So this is your NPN transistor, and this NPN transistor is basically defined in the common emitter configuration because the emitter is common. And with the help of symbol, you can also draw this configuration. This is emitter, and here we are having collector terminal, and this is your base terminal. So as you can see, for all the configuration that is happened, the emitter base junction must be forward bias and the collector base junction must be reverse bias. So if this is N and this is P and this is N, that means emitter base junction must be forward bias. So you have to apply a positive voltage at the P terminal, that means base terminal, with respect to the emitter terminal. So here this resistance is RP, and you have to apply a positive supply, or you can say the positive voltage at the base terminal. This is defined as VB. If we discuss about the common base configuration, the common base must be reverse bias. That means you have to apply a positive voltage at the collector terminal with respect to the emitter terminal. Plus minus VCC, and this output voltage is VCE, and the current to the collector terminal is IC. And here we will discuss about the base. This is IE. IE is equal to the IB plus IC. That means this is the direction of IB. So as far as KCL rule is concerned, if you will apply the KCL for this circuit, we will get IE is equal to IB plus IC. But this is only KCL. Is that clear? This equation will never describe the circuit operation. I'm again repeating, as far as active region is concerned, this is only KCL rule. IE is equal to IB plus IC. But if you want to describe transistor action, in the transistor for the active region, it is well known to all of us, IC must be equal to IE. So if emitter current is 1 milliampere in the active region, that means collector current is also 1 milliampere. If the emitter current is 2 milliampere, that means collector current is also 2 milliampere. But this is for the ideal transistor. If IC is not equal to IE, it is well known to all of us, IC is equal to alpha times IE, where alpha is the current gain. or you can say current amplification factor for the common base configuration. But here, for the common emitter configuration, if you want to determine the current relationship, that means relationship between the input current and the output current, how we can determine, we will discuss the detail. Right now, you have to focus on this configuration. This is basically common emitter configuration. This configuration has been drawn with the help of symbol, and this is drawn with the help of ambient structure. So now here, we will discuss about the current relationship for the common emitter configuration. So now here we will discuss about the current relationship. In CE configuration. Current relation in CE configuration, that means for the common emitter configuration, we want to determine the relation. What is the relation between the input current and the output current? So as far as common emitter is concerned, the emitter is common for the base as well as for the collector. So here, this is base and this is collector, and emitter is made common. So this is your input side and this is our output side. So if anybody asks you what is the input current in the CE configuration, the input current is IB. What is the output current? Output current is IC. What is your input voltage? Input voltage is VBE, base to emitter voltage. Output voltage VCE. And we want to determine the relationship between the input current and output current. So input current is IB and the output current is IC. That means you want to determine the relation between the IB and IC. And in the transistor, we are having two basic equations. First is from KCL law. I is equal to IB plus IC. As far as activity is concerned, if you want to discuss, if you will discuss about the transistor action, the IC is defined as a alpha time IE plus ICBO, where ICBO is the collector to base leakage current. Collector to base leakage current. O stands for open. That means whenever input junction is open, is that clear? Now look at here. I is equal to IB plus IC. This is equation number 1. And the IC is equal to alpha time IE plus ICBO. This is equation number 2. And we want to determine the relationship between the IB and IC. So here IE must be eliminated. Is that clear? That means from equation number 2, we will determine the value of IE, and this value we will put in the equation number 1. So here, in place of IE, IC minus ICBO divided by alpha, this is the value of IE. And this value must be put in the equation number 1, so that IE can be eliminated. Is that clear? So here, in the equation number 1, equation 1, if you will put this value, IC divided by alpha minus ICBO divided by alpha is equal to IB plus IC. Now here, if you will rearrange this equation, what we are getting, look at here, IC divided by alpha and this is IC. So IC is made common, and here we are having 1 minus alpha divided by alpha. Is that clear? And this is equal to IB plus ICBO divided by alpha. This is very simple derivation. So here, if you will determine the value of IC can be written as IB alpha divided by 1 minus alpha and plus alpha divided by alpha ICBO divided by 1 minus alpha. Alpha would be cancelled out. So this is the expression. Is that clear? Let us assume a new factor which is defined as a beta is equal to alpha divided by 1 minus alpha. If we will add 1 at both sides, 1 plus beta and alpha divided by 1 minus alpha plus 1, we are getting 1 divided by 1 minus alpha equal to 1 plus beta. Is that clear? So here 1 plus beta is equal to 1 divided by 1 minus alpha, and we are assuming beta is equal to alpha divided by 1 minus alpha. Is that clear? If we will put the value of 1 divided by 1 minus alpha in this equation, and we are assuming alpha divided by 1 minus alpha, here this equation is now become or can be written as IC is equal to beta times IB plus 1 plus beta times ICBO. Is that clear? And that is known as a reverse leakage current. For the common emitter configuration, this current can also represent as ICEO. Collector to emitter leakage current when input is open. ICEO is equal to 1 plus beta times ICBO. That means IC is equal to now beta times IB plus ICEO. So this is the collector current for the common emitter configuration. As it is well known to all of us, base collector to emitter leakage current, the magnitude of this current is very small, so you can neglect this current. You can also neglect this current. So if you want to determine the value of beta, IC is equal to beta times IB. You can write the value of beta as IC divided by IB, where beta is your current gain. Beta is your current gain for the common emitter configuration. Is that clear? And beta is equal to alpha divided by 1 minus alpha, and it is known to us alpha values is lying between the range of 0.95 to 0.99. Basically the value of alpha depending upon the thickness of the base. So in alpha, if you will consider as 0.99, if the value of alpha put it in the expression of beta, you will get beta is equal to 99. So the current gain in the common emitter configuration is very high compared to the common base configuration. So this is the advantage of common emitter configuration. And what is the application of NPN transistor as far as common emitter configuration is concerned, we will discuss after some time. Is that clear? Now this is the current relationship. Now we will focus on input and output characteristics. We will focus on input and output characteristic of transistor in the common emitter configuration. So firstly, we will discuss input characteristic. After that, we will focus on output characteristic of transistor. So here we will focus on input characteristic in CE configuration. CE configuration. So we are already aware how we can draw the input characteristic. Input characteristic for any given transistor is drawn between the input voltage and input current for the given value of output voltage. So firstly, you have to define the input voltage and the input current and the output voltage for the particular configuration. So as you can see, emitter is common for the base as well as for the collector. So this is your base and this is your collector. So the input current is IB and the output current is IC and the output voltage is VCE, because this is your input side and this is your output side. So output voltage is VCE, output current is IC, input current is IB, and the input voltage if you want to determine VBE. So we want to draw the input characteristic. So input characteristic is always plotted between the input current and the input voltage for the given value of output voltage. Is that clear? Now, it is well known to all of us. We will discuss about the NPN transistor. We want to draw it for the NPN transistor, and the same principle is applicable also for the PNP transistor. You can also draw the characteristic for the PNP transistor once you understand how we can draw the input characteristic of NPN transistor in CE configuration. So input voltage is VBE, given in the volt, and the input current is IB in microampere, because the magnitude of the base current is very small. It is in microampere, and this characteristic has been drawn for the common emitter configuration for the constant voltage, and this voltage defined as VCE, and this is VCE. And it is well known to all of us, in the NPN transistor, the input junction is nothing, it is PN junction. And how we can draw the characteristic of the PN junction diode? It is very simple. The current is allowed to flow whenever the voltage applied at the input terminal, that means base terminal, is greater than 0.7 volt for the silicon transistor. For the germanium, the voltage applied at the base terminal must be greater than 0.3 volt. So this is your input characteristic. So how the current is going to be changed depending upon the input voltage as well as depending upon the output voltage, we will discuss. Now look at here. This is the structure of N, P, N. This is your collector terminal. Okay. Let me draw it in common emitter mode. This is N, this is P, and this is N. Depletion region, depletion region. Look at here. This is collector, this is emitter, and this is your base terminal. So what is going to happen? If you will increase the collector voltage, that means you are increasing the reverse bias voltage, because the collector base junction is reverse bias. So if you will increase the VCE, you are increasing the collector to base voltage, you are increasing the reverse bias voltage. So somewhere the width of the depletion region is going to increase, and it is well known to all of us, the width depletion region is going to be extend, or it can penetrate more from higher doping towards to the lower doping. So the base is thin and it has lightly doped. It has lightly doping. So what is going to happen? The depletion width is going to more penetrate into the base region. So base is now more thin. So somewhere the base current is going to increase if you will increase VCE. Is that clear? So here the VC is equal to 10 volt and here the VC is equal to 5 volt. So this is your input characteristic for the NPN transistor in common emitter configuration. Now we will discuss about the output characteristic. The output characteristic is plotted for the output voltage and output current. The output characteristic of transistor is plotted between the output voltage and output current. So here, as you can see, the output current is IC and the output voltage is VCE. That means we want to draw the characteristic between the IC and VCE for the given value of input current, and the input current is IB. So here on this x-axis we are having the output voltage, this is VCE in volt, and on y-axis we are having IC in milliampere. As far as VCE, or you can say the saturation region, is concerned for the transistor, this is approximately, this characteristic is for NPN transistor. The saturation voltage, that means VCE saturation, it has been so many experiments is performed, and it is known to us the VCE saturation is defined as 0.1 volt to 0.2 volt for any given transistor. In the saturation region, emitter base junction is forward biased and the collector base junction is also forward biased. And the current is going to decrease. It is well known to all of us in the saturation region. So as far as activity is concerned, if this value I is equal to 0 milliampere, And if you will assume I is over here is equal to 10 milliampere, I is equal to 20 milliampere, and here I is equal to 30 milliampere. So for the active region, IC is approximately equal to IE, and it is well known to all of us IC is equal to beta times IB plus ICEO for the common emitter configuration. If IE is equal to 0, this is also equal to 0, and that region is known as cutoff region. So here IC is equal to ICEO. And IE is equal to 10 milliampere, that means IC is also equal to 10 milliampere. If I is equal to 20 milliampere, that means IC is also equal to 20 milliampere. If I is equal to 30 milliampere, that means IC is also equal to 30 milliampere. We have introduced some slope because there is an addition of collector to emitter leakage current. In the saturation region, what is going to happen? The current is going to be decreased and decreased. So here this region is defined as a saturation region. This region is defined as an active region. And that region is known as saturation region. So in the active region of the transistor, it is well known to all of us, input and output current are same. So if the input current is 1 milliampere, output current is also 1 milliampere. So this is the output characteristic of NPN transistor in common emitter configuration. Similarly, this characteristic can also draw for PNP transistor. What is going to happen? Only voltage polarity is going to be changed. Is that clear? Now, we will discuss about another configuration. This is defined as common connector configuration. Common collector configuration. So as the name implies, common collector. Collector is made common for the base as well as for the emitter terminal. So here, this is common collector configuration. This terminal is collector made common. Let me draw this configuration for NPN transistor. So here this is N. This is your depletion region. This is your depletion region. This is P. And here we are having N. This is your base terminal. And this is your emitter terminal. So the collector is common for the base as well as for the emitter. So you can apply the input voltage at the base terminal with respect to the collector terminal, and we are getting the output voltage at the emitter terminal with respect to the collector terminal. For all the configuration, it is well known to all of us. We have to operate the transistor in active region. That means the emitter base junction is forward biased and the collector base junction is reverse biased. So if you want to make it input junction is forward biased, that means you have to apply a positive supply at the P terminal with respect to the emitter terminal. Positive plus minus, and here you can also introduce a resistance RB, and this voltage VBB. We will discuss about the collector base junction. It must be reverse biased. As you will make it is forward bias plus, that means this is minus. There is a negative with respect to the collector terminal. So this is minus plus. You can also introduce RC, which is your current limiting resistor, and this is known as VEE. So this is common collector configuration. As you can see now here, the input junction is collector base junction, or you can say the base collector junction, and the input junction is reverse biased. So if the input junction is reverse biased, if you want to make transistor on, you have to apply the voltage which must be greater than 0.7 volt for the silicon transistor. So here the input impedance is very high. For the common collector configuration, so basically common collector configuration is used for the impedance matching. Is that clear? The same configuration you can also draw with the help of symbol. Is that clear? Now look at here. This is your transistor symbol. The direction of current is always indicated with the help of emitter terminal. So this terminal is emitter and here this terminal is collector and the collector is common for the emitter as well as for the base. So emitter base junction again is forward bias and the collector base junction is reverse bias. Is that clear? For the common collector, the input junction is reverse bias because there is a VCB is your input junction. So input impedance is very high. We are using the common collector configuration is basically for the impedance matching. Now we will determine the current relationship for the common collector configuration. In CC configuration, common collector configuration. So the collector is common for the base as well as for the emitter. So this is your input side, this is your output side. So input current is IB, input voltage is VBC, output current is IE, the output voltage is VEC. So we want to determine the current relationship between the input and output current. So input current is IB and output current is IE. So you have to eliminate IC. So it is well known to all of us. IE is equal to IB plus IC and IC is equal to alpha times IE plus ICBO. And we want to eliminate collector current, that means IC. Is that clear? Now look at here. Put the value of IC over here. Or you can say put the value of IE over here. Sorry, IE, we want to eliminate IC. So put the value of IC over here, we will get IE is equal to the IB plus alpha times IE plus ICBO. So here if you will take IE common, this expression is now become or can be written as IB divided by 1 minus alpha plus ICBO divided by 1 minus alpha. In the previous configuration, we have already determined the value of 1 divided by 1 minus alpha. This is equal to 1 plus beta. So here I is can be written as 1 plus beta times IB and plus 1 plus beta times ICBO. And the 1 plus beta we are assuming or defined as a gamma. So let us assume gamma is equal to 1 plus beta. So you can write the expression now as I is equal to gamma, where gamma is your current gain or the current amplification factor for the common collector configuration as IB and plus gamma times ICBO. So gamma is very high. The current gain in common collector configuration is very high. Is that clear to you? So this is the current relationship for the common collector configuration. Now we will see how we can draw the output characteristic. Output characteristic of NPN transistor in common collector configuration. Is that clear? The output characteristic is similar to the output characteristic of transistor in common emitter configuration. Only output current is going to be changed because in the active region the IC is approximately equal to IE. So in the previous output characteristic, IC has to be replaced by IE and the characteristic will be same. IE is given in the milliampere and the output voltage now become VEC in place of VCE. This is in volt and the characteristic is same. Is that clear? This is your cutoff region. Cut off region. This region is now become active region and this region is now become saturation region. Is that clear? So the output characteristic for given transistor in the common emitter configuration as well as in the common collector configuration are always same. Now, we'll discuss about the current relationship between the alpha and beta. Relationship between alpha and beta. And this is very important. Is that clear? It is well known to all of us. IE is given as IB plus IC from KCL. I is equal to IB plus IC. This is equation number 1. And it is also known to us alpha is equal to IC divided by IE if we will neglect the base collector to base leakage current. So here alpha is equal to IC over IE and beta is equal to IC over IB if we will neglect collector to emitter leakage current. So alpha is given as IC over IE, beta is equal to IC over IB. If equation number 1 is divided by IC, here we will get IE divided by IC, IB divided by IC plus 1. So IE over IC can be written as 1 divided by alpha. IB over IC can be written as 1 divided by beta, and this is plus 1. And if you will solve it and if you will rearrange it, what we are getting? Beta is equal to alpha divided by 1 minus alpha. Is that clear? And you can also define the value of alpha in terms of beta. Is that clear? So beta is equal to alpha divided by 1 minus alpha, and this current relationship is very important. Is it okay? Now, we will discuss about the numerical problem. Most of the time, if alpha is given as a 0.95, they will ask the value of beta. So beta is equal to alpha divided by 1 minus alpha. You can determine the value of beta. Similarly, IC is equal to alpha times IE plus ICBO. Alpha is given, IE is given, ICBO is also given. You have to determine the value of IC. It may be possible alpha is not given, beta is given. You can determine the value of alpha. Now, we'll discuss about DC biasing. DC biasing of transistor. So firstly, we will discuss what is biasing. Biasing is the process in which we are applying external voltage to any device. Here in this case, we will apply the external voltage to the transistor, and that voltage is DC because we are interested in DC biasing. We will discuss about the AC. You have to apply a AC voltage to the transistor. Is that clear? So why we are using the biasing? With the help of biasing, the region of operation for any given transistor can be defined, because it is well known to all of us transistor can be used as amplifier in active region. Transistor can be used as an open switch in cutoff region, and transistor can be used as a closed switch in saturation region. So as far as saturation and cutoff regions are concerned, transistor is used as a switch. And in the active region, transistor is used as an amplifier. So the region of operation you have to change. And how it is possible? By changing the location of operating point on the region of characteristic. And for that purpose, we are using the DC biasing. Is that clear? But before started, or you can say before started discussion on the DC biasing, we will focus on the DC load line concept. How we can draw the DC load line on the region of the characteristic, and how we can determine the location of operating point. Because for any given characteristic, as far as region of characteristic is concerned, there are so many operating points. So which operating point is more suitable according to the application of transistor in different region? active region, saturation region, and the cutoff region. That point has been decided or will be decided with the help of DC biasing. So before started DC biasing, we will discuss or focus on the DC load line. DC load line. We will discuss about the transistor configuration. There are three configurations: common base, common emitter, and the common collector. As far as amplification is concerned, common emitter is best configuration because the current gain as well as the voltage gain are moderate. In the common collector, no doubt the current gain is high, but the voltage gain is less than 1. For the common base configuration, no doubt the voltage gain is high, but the current gain is alpha, less than 1. Is that clear? So here the common emitter configuration is the best configuration as far as the amplification is concerned, because the voltage gain as well as the current gain are moderate. Is that clear? So we will draw the DC load line for the common emitter configuration. Is that clear? We will draw the DC load line for the common emitter configuration. So here the emitter is common for the base as well as for the collector. This is RC, and here this is positive supply, this is ground, and here we are having RB, and this is positive, plus minus VBB, and this is plus minus VCC, and let us assume the output current is IC, which is flowing through the collector terminal, and the output voltage is VCE. So we want to draw the load line, that is DC load line for the output characteristic, and the output characteristic is plotted between the output voltage and output current for the given value of input current. Is that clear? So here the output voltage, if you will apply the KVL, you can directly write VCC minus IC into RC. This is the picture. Is that clear? This is the relationship between the output voltage and the output current for the given power supply VCC. So here VCE is equal to VCC minus IC into RC. If you will rearrange and determine the value of IC, you can written as VC minus VCC divided by RC divided by RC, and here this is IC. Now this is minus and this is plus. Is that clear? So IC can also define as a minus 1 divided by RC into VCE plus VCC divided by RC. Is that clear? Now look at here. This is the slope. If you will compare it from the straight line equation, y is equal to mx plus c. M is the slope. Minus 1 divided by RC. X represented VCE, output voltage. And VCC divided by RC is constant, C. So this equation will represent a straight line. That means on the output characteristic of the transistor, you have to draw a straight line, and the maximum point as well as the minimum point can be determined. If we will put IC is equal to 0, VCE max is equal to VCC. If we will put VCE is equal to 0, the IC will be maximum, and the IC maximum you can determine as VCC divided by RC. Now, if you will draw a straight line under the DC operating condition on the output characteristic of transistor, this is VCE, this is IC in milliampere, this is in volt, this is the characteristic. Is that clear? For the given value of input current IE, this is IE, this is IE, 0, 10 milliampere, 20 milliampere, 30 milliampere, 40 milliampere. So the maximum, IC maximum is equal to VCC divided by RC. So let us assume this point is corresponding to the IC maximum, and this point is corresponding to VCE maximum. Is that clear? You have to draw a straight line, y is equal to mx plus c. Is that clear? So this is basically DC load line, because this line has been drawn under the DC operating condition. in the absence of any AC input. Is that clear? So this point, this point, this point, this point, this point, all these points are defined as the operating point Q1, Q2, Q3, Q4 and Q5. And depending upon the biasing, if you will apply now AC voltage for the positive of cycle, Q point can be shifted upward. For the negative cycle, Q point can be shifted downward. That means the location of Q point must be selected according to the region of operation. In which region you want to operate transistor. So this is your DC line. As far as amplification is concerned, the location of operating point, or you can say Q point, must be lie in the middle of the characteristic. If you want to use transistor as an off switch, the Q point must be lie in the cutoff region, because this is cutoff region. This is your active region and this is your saturation region. So if you want to use transistor as an on switch, your Q point must be lie in the saturation region. Is that clear? So with the help of biasing, what we can do, we can change the location of operating point according to our application. In which area you want to use transistor. Whether you want to use transistor as a switch or you want to use transistor as an amplifier. Thank you.